This assignment assisted us in our learning because it involved the use and interpretation of multiple standards such as AS 1170 and AS 1170.1 for structural design actions, as well as AS 4055 for wind loads for housing. Using the specifications provided to us for shielding, topographic area, wind region and shielding, we determined that our structure would be in a non-cyclonic area with a wind class of 4. Purlins were designed to accommodate for the dead loads, live loads and wind loads acting on the structure. Firstly, the dead loads for the roof cladding, insulation, ducting, suspended ceiling and self-weight of the purlin were determined and combined to find the minimum and maximum dead loads. Secondly, the live load was determined using the formula Q equals 1.8 over A plus 0.12 as provided in table 3.2 of AS 1170.1. Thirdly, the wind load was determined using the pressure coefficients for ultimate limit state. The formula P equals QU by CP is used to determine the wind pressure, where QU is a free stream dynamic wind pressure and CP is a pressure coefficient. The values for QU were found in table 2.1a from AS 4055 and the pressure coefficient values were found in table 3.1 from the same standard. We were able to determine values for pressure and suction forces acting on the roof using this formula. Finally, the critical load combinations were determined using 5 load combinations set out in section 4 of AS 1170. The critical load combinations acting on our purlin were 1.836 kilopascals of pressure and negative 2.1527 kilopascals of suction. These values were compared to our design capacity table to determine if the selected purlin design, in this case Z15024, was safe to use. The design did require one row of bridging to prevent flexural torsional buckling and limit deflection of the purlin in the direction of its weak axis. The serviceability of the selected design was checked to confirm whether the design was safe to use. The same steps are followed to design the girts. However, upon receiving feedback from part 1 of our report, we learnt that only the wind load needs to be considered. Initially, we included dead loads for the components of the wall, but since the dead loads and wind loads are acting perpendicular to each other, they cannot be added together. As I completed the bracing design, I learnt that bracing is required to resist lateral loads arising due to wind loads acting on the structure. Roof bracing is used to transfer the lateral loads to the wall bracing and then to the foundation. Single member bracing was designed to support the loads in compression and tension. The diagonal bracing subject to compressive forces was eliminated for the purpose of this report. To design the bracing, the racking or lateral forces acting on the structure must first be determined. This was achieved using the equation provided in section 5 of AS 4055, where the area of elevation is multiplied by the lateral wind pressure. The area of elevation is half the height of the structure multiplied by half the distance between the two adjacent columns. Lateral wind pressure or suction acting on the windward and leeward walls was determined using P equals QUCP again, remembering the CP value will be different for the wall and the roof. It is important to note that the forces acting on the intermediate frame and end frame are considered separately. Using the lateral forces found, the maximum compressive and tensile forces acting on the roof bracing could be determined. These forces were determined using hand calculations as well as space gas to support the results. The hand calculations reinforced knowledge learnt in Structures 1, where equilibrium of a body and equilibrium of joints were applied to determine the critical forces acting along each member. The negative and positive values meant that the member was in compression or tension respectively. These values found enabled our group to select the correct bracing design to support compressive and tensile forces acting on the structure. The roof bracing is supported by the wall bracing. The reaction of the roof bracing is in fact the lateral force used to design the wall bracing. Again, equilibrium of a body and joints was used to determine the correct bracing design. To summarise, circular hollow section 60.3 by 3.6 was selected for the struts since it was in compression and its design capacity exceeds the critical compressive force found. The design selected is therefore safe to use. 50 by 50 by 3 each angle, grade 300, was selected for the diagonal bracing for both the roof and walls. This was because its tensional design capacity exceeds the critical tensile force acting on it. Therefore, the diagonal bracing design selected is safe to use.
Hi, my name's Justin and I'll be talking about designing a typical column. Columns are a vertical member of a structure that is subjected to vertical compressive loads. They are used in a structure for supporting and transmitting the horizontal loads from the ceiling, roof slabs and beams to the concrete footing supporting the structure. In order to design a column, 8 steps must be followed to ensure a column member selected is both safe and able to withstand the loads associated with the structure. Columns are designed to accommodate for dead, live and wind loads that a building may be subjected to. Throughout this process, I've learnt that when designing a column, the connections for a braced box structure should have pin joints, and therefore this does not require you to consider the lateral or wind loading that would affect a structure. The other steps taken to design a column include the load combinations for ultimate limit state, designing for buckling capacity, moment capacity, and also checking the column's capacity for the combination of both compression and bending moment. The final step of designing a column is to check for reversal actions under tension. For our structure, the universal column member that was chosen to support the central rafter was 100 UC 14.8. The capacity of this member is 111 kilonewtons, and the maximum compression force needed in the column for our structure was 32.1244 kilonewtons. This member was the smallest universal column on the capacity table, and I found it was a safe option to use. Although it is not very economical, there was no other smaller member with a lower capacity to use. Therefore, 100 UC 14.8 was selected as the best option to support the central rafter.
Rafters are structural members that are designed to support the roof loads of the deck. To design the central and end rafters in our structure, steps must be followed to ensure the rafter section selected is safe and can withstand the associated loads. When designing the rafters, it is important to note that the roof pitch does not come into consideration, therefore rafters may be referred to as beams. Horizontal members of the structure are also used to resist bending moment. The top chord of the beam is under compression and the bottom chord is under tension. Both need to be considered in the design process to ensure the beam does not buckle laterally or torsionally. When designing the rafters, you must calculate the dead load, live load and wind load. These values will be times by the supported area of the rafter to give a uniformly distributed load on the beam. For the central rafter, that width is 5 metres. The critical load combination is used to find the moment capacity of the beam both under compression and suction, which is used to choose a suitable UB section that is safe and economical. The universal beam section chosen was safe in compression, however not safe in tension. This meant that the use of fly bracing could help strengthen the bottom chord of the beam. Interpolation was used to determine the moment capacity of the beam with the fly bracing on the rafter. It was also important to check the self-weight of the UB section to ensure it is not too heavy for the associated load. The serviceability limit state is checked by calculating the maximum deflection of the beam, which has to be less than the Australian standard of 26 metres. The end rafter is calculated in the same way, however the width of the supported area is 2.5 metres. The UB section chosen for the central rafter was 250 UB 37.3 and the section chosen for the end rafters was 250 UB 25.4.